Unit 2, projectile motion and free fall, involves basically a lot of kinematic workups of problems that look just like this. Let's say that we have a ball that's dropped from an elevated position, and perhaps we can ask questions about what time does it take to strike the ground, what distance did it travel before hitting the ground, but a lot of this just has to do with basic kinematic workups, vocabulary which we learned in Unit 1. Okay. Let's talk about each of these and how they applies to the problem. The one phrase that we want to be looking out for a lot in this unit and just in general moving forward is from rest. From rest means that we dropped the object with no vertical velocity component. So anytime that you see something from rest, you kind of know what your initial velocity is going to be, 0. All right, another component that we kind of already know just based on looking at where things are headed is our acceleration. The acceleration given is the acceleration due to gravity on Earth. In this class, we'll make that number -10 meters per second squared. Keeping a close look on that directionality component, falling downward means that those are negative numbers, or traveling downward insinuates that those are negative numbers, whereas upward would, of course, be positive. Now, final velocity you could solve for. A lot of folks will say, well, we're dropped from rest, and once it hits the ground, it's at rest, so that will be 0. Those people are wrong, and that's wrong. The final velocity refers to the velocity with which it strikes the ground. Now, we can say, with common sense and logic, that it'll probably be a negative number here, but we don't know what that is. Time, of course, just referring to the time required to reach the ground, and distance. If your distance is given in this problem where you solve for a distance, make sure that it's right by making sure that it's a negative number. Negative distance in meters. The next topic that this unit addresses is parabolic motion. Now, there's several different types of parabolic motion problems. We'll start with the easiest type, which are problems which happen to be what I would phrase perfectly parabolic. That is to say that the object is launched and then arrives at the same elevated position from which it was launched. Therefore, you can conclude that the time required to reach the midpoint is equal to the time required to reach the end. The maximum height reached is the same on both ends of our dome. And there's 3 equations which you can use to solve for things with perfectly parabolic problems. And here they are. Boom. You got how to solve for the amount of time required to reach, your destination. This angle theta here refers to the angle of launch. And that initial velocity there refers to the resultant initial velocity with which an object is launched. Just dealing with our weird, exponents and angles and whatnot. This squared means that this whole function is squared once you get your answer, and that 2 there means that you multiply your angle by 2 before plugging it into your calculator. Using these 3 equations, you can solve for the required time to reach your destination, the maximum height reached by that launch, and the maximum distance horizontally reached by that launch. Finally, this unit ends with parabolic launches, which are not perfectly parabolic. In these such problems, you may be launched and you're landing at an elevated position or a perhaps lower position or whatnot, but you don't land at the same height from which you were launched. The first steps in order to do problems such as this are to realize that we've made a trigonomic reference right triangle with regard to our initial velocities of launch. You will be tasked with breaking that initial velocity down into its horizontal and vertical components using trig. Typically, you're given, for example, the initial velocity. You're given, for example, this angle here. And you could go about solving for your vertical component of motion of initial launch and your horizontal component of motion for initial launch. Using trig for the horizontal component, and this can very well just be memorized instead of having to relearn the trig or try the trig every time for the horizontal component of motion. Rearranging that, we could essentially say that our resultant velocity with which we were launched times cosine of theta will equal our horizontal component of motion. Ditto on the vertical component of that motion. Finally, we would open up a series of kinematic variables which pertain specifically to this situation. You have variables that relate to the x component, for example, of motion. And the x component of motion, you have a distance traveled horizontally, essentially this distance right here. Horizontal distance of motion can be outlined using a DST. We're able to use a DST instead of a kinematic approach to our x components of motion because at any arbitrary instance along this parabola, the horizontal component of velocity will be the same. We don't accelerate in the horizontal direction. We don't speed up and slow down. So that's how we're able to just make that a simply DST triangle. Variables which apply to this, for example, speed, we've kind of already solved for our speed. That would be VI cosine theta is going to be equal to our VIX. And that VIX is a little misleading. We could very well just call that VX because there is no acceleration there. Aside from the x variables, we have up and down components to this problem. Up, y up, and y down. Kinematic workups of both ends, since we are accelerating in the vertical directions, look like this. Now, just drawing upon common sense in which variables apply in which situation, VI we've solved for earlier. That was going to be VI, our resultant initial velocity, times sine theta. I guess I should call this VIX, right, or VIY right there. The acceleration we know is going to be negative 10 meters per second squared on both ends of the y. Because whether you're traveling up or you're traveling down in the y direction, your acceleration is constant, negative 10 meters per second squared. Logically, for the up component of that final velocity will be 0 meters per second. Well, because at the top of the peak, at the top of that peak over there, you're not moving well in the y direction. You still have your horizontal or x component of motion, but in the y component of motion, you are motionless. And then you can use those such three variables to solve for time required to reach the top of the parabola and the maximum distance reached by that top of the parabola. For the y down components, we know that the initial velocity is 0 because the same reason why VF was previously 0. At the top of the peak, you are not traveling with any velocity as it pertains to the y direction. But we don't know these three variables. Now, you would probably use logic in order to solve for one of these three kinematically, and then use that to plug in to solve for the other two variables, realizing that your total time of motion for these such problems is your y up and y down added together, and then realizing that logically, so the time for y up plus the time for the y down is equal to the time required that you have to work with in the x direction. And then perhaps you would be tasked with solving for the distance traveled. We'll work with a variety of problems such as this so that way you can practice this topic. I realize it's a little confusing at first, but after muscling through 3 or 4 problems, you should get it under your belt and be all good with it.